Hi people, welcome back. As I said in the previous lesson there, that lesson was so long in terms of megabyte in size, so I've um, decided to do this question in 2 bits. Okay, otherwise it's just too big. So we've done the position of the centroid, where we determine x left, x right, and y top, y bottom. And then we've done that massively long ixx and iyy. And now we're going to work at the radius of gyration about both axes, and then the section modulus about both axes, and then we're done. Okay. Now remember when I spoke to you about the note in the introduction, there's the note. The radius of gyration, its symbol is the small letter r. I'll just quickly read it here. It's very sort of, what's the word? It's very, I forget. If all the area of a section could be concentrated into a single dimensionless point, which is impossible actually, without altering the value of the second moment of area by the given axis, then the distance between this point and the axis would have to be equal to r, which is the radius of gyration, which is given as the square root of, this is the general formula here, the second moment of area divided by the total cross-sectional area of the section. And the radius of gyration is used in the design of compression members, that is columns, such as columns and arms, such as columns and struts. And then it goes on further to say that slender compression members, slender just means that if you look at the cross-sectional dimensions of a column in relation to its length, okay, I mean, the area of a column is normally very much smaller than the length of the column. And if that's the case, if it's within certain dimensions or ratios of those dimensions, which we say is the slender column. Slender compression members fail by buckling. That means bowing out to one side or the other, rather than crushing or shearing, and tend to do so about the axis for which the radius of gyration is a minimum value. So all I want to say at this point, and that's a bit of a mouthful. That's very I forget. I can't get the word now. It's a design thing. So when you get to the design of actually loaded columns, okay, one of the checks you do in the design is to check for minimum radius of gyration, okay, and that's the formula we're going to do here. So all we're going to do is work at rxx and ryy, which I'm going to do now. Okay, right. So point C, so rx, so rxx is equal to Ixx over the total area of the section, like so. And of course, Ixx we found to be 1.0, okay, 1.06 times 10 to the power 7 over the total area, and the total area was 5,400 square millimeters, and I'm going to divide it all like so. Okay, can you predict what the unit of measurement should be? Yeah, because it's a straight distance, it should be millimeters, because millimeters to the power 4 divided by millimeters squared gives a millimeter square, and the square root of that should just be millimeters. So if I work that out and you do your calculation, you should get something like, did I do it? Yeah, I get 44.31. 44. Okay, and that's it. Okay, so that's the radius of gyration about the x-axis, and then ryy is equal to the square root of iyy over the total area. And what's iyy? I'm going to write it out fully because I'm going to account for all these decimals there. 4 iyy is over the total area, which is the same for any one given section. And if I work it out, that gives me 29.54 millimeters. 29.54 millimeters. Okay, that's it. Okay, so that's the radius of gyration about both the axes. But often in a question, I ask you to calculate R min, okay, or R minimum. Why am I asking you to calculate R minimum? Because if you go to the notes there, it says there that slender compression members fail by buckling rather than crushing. Buckling just means, if I can draw it out, if you have a column, I just talk about that. If we have a column, for example, let's say there's a column there, thin column like so, and it's undergoing a compressive load, okay, and that there is the longitudinal axis along the column. And if it's very thin, that if it's tall and if it's small in cross section and very thin, it will either bend to one side like so, or one side like so. Okay, if the column is squat, that means it was very fat but short. Okay, it can't fail like that. Now, what it does, if I look at it in section, it might fail like something like if I look at it like so, it might fail something like okay, and if it's undergoing a compressive load like so, okay, and if the column is squat, that means very short, okay, it can't fail by buckling, it will fail by crushing. That means it will just shear there. The word is shear, okay, and one bit of it will just break off and move down to that side, and that will move some into that side there, okay. So that's failing by buckling, and that's failing by crushing, okay. That's it in sketch form there, okay. So if a column, so slender compression members fail by buckling rather than crushing or shearing, that means in that case over there, okay, and tend to do so about the axis for which the radius of gyration is a minimum value. So often I will ask you to work at R min, and what you do is you work at these two values here, or what you do is R min basically is the smaller of the two I values, which is this one here, over the total area, is 29.54. Okay, so R min for this particular section there would be that value over there, the smaller of the two. Okay, so R min is equal to the smaller of the two I values divided by A, square root of the lot, is that over there. Okay, so that's the radius of gyration for those two there. And then the last question says work out the section modulus about the XX and the YY axis, which I'm going to do now. Right, people, for section modulus, there's actually 4 sets of calculations, quick ones. Let me go back to the note. I'll go down to the note there. There we go. Section modulus. I'm going to read the definition there. Now, the design concept. In problems involving bending stresses in beams, including the design of beam sections, a property called the elastic section modulus, or what we sometimes often say the section modulus, is used to express the bending moment stress relationship. Okay, this may be treated as a geometrical property. Theoretically, each point within the cross-section of a beam will have a section modulus, this simply being the ratio of the second moment of area, which is I, to the distance between the point in question and the relevant axis. Okay, so basically, generally, Z is equal to I over Y. Okay, generally. Okay, but these are specific section modulus, but we're gonna do ZXX and ZYY. So let's do it. So Z is generally equal to I over Y. So ZXX is equal to I XX over Y. Okay. But people, have a look at the sketch here. There's a Y top and a Y bottom. So we're going to consider both of them. So I'm going to name this one like this. Okay. So ZXX regarding Y top is equal to that over there. So that's going to be a 1.06 times 10 to the power 7. I'm just squeezing one. And what's Y top equal to? 101.67, 101.67, and I work that all out. The answer I get is, if I do a calculation quickly, it is equal to 1.043. It is 1.043 times 10 to the power 5. Have you guessed what the unit of measurement for section modulus should be? That's millimeters to the fourth. That's millimeters, so that's going to be millimeters cubed. That's right. And it is not a volume. Notice it's also a volumetric dimension, but it's not a volume. It's also section modulus. Okay. Right. Now we're going to do ZXX with regard to Y bottom. So I'm going to name it like that. And you can see where this is going to. It's simply going to be that divided by 48.33. So it's 1.06 times 10 to the power 7 over, oh, what a bad line that was. Y bottom 48.33. And if you do the calculation, just don't believe me, work it out for yourself. See what you get when I do. And I get 2.193. So I get 2.193 times 10 to the power 5 millimeters. If you leave at the units, I take a mark off. If you make it millimeters to the fourth, I take a mark off. If you make it millimeters or millimeters squared, I take a mark off. It's millimeters cubed. Right, people. But we need to calculate ZXX and ZYY. So we're gonna, so you can see where this is going. Okay, and what Z generally is equal to I over Y, but in this case it's I over X. Okay, because it's about this axis here, so therefore we're concerned with the distance about the y axis. But there's two X values, so I'm going to do the left one first. So there's going to be X left, so it's going to be IYY, which is, and I'm going to write the full value in, so I can take all those digits, is 4713, 471. Or you can write, or you can use the 1/4 scientific notation, that's quite fine. X left is 32.22. And that is equal to, let me just see, what did I get? 1.463. 1.463. Stop the video here, work it out for yourself, and see if you get what I get, times 10 to the power 5 millimeters cubed. If you get small discrepancies here, if you get 1.463 or 1.45, that's fine. And then the last one, ZYY with respect to X right is equal to IYY over X right is equal to 4713,333. If you want to put in the 0.36, whatever it was there, X right is 67.78, and that should be equal to 6.954, 6.954 times 10 to the power 4 millimeters cubed. Okay, people, we have answered the whole question. Now you can see there, that's one question, and it's only for an L section. It's only for an L section. If this one had another leg or arm going this way, and there was voids in there, like circular voids or semicircular voids or triangular voids or triangular bits, this question gets a whole lot longer and more complicated and more room for mistakes. Okay, so people, there I've just done RX and RYY, and I've just done ZXX and ZYY. Okay, ZXX has got two bits to it, because there's a Y top and a Y bottom, and notice there With ZXX, we're working about the XX axis, so we're concerned with the vertical distance, y top, y bottom. And ZYY is bending about the y-axis, so we're concerned about distance about the y-axis, which is x left and x right. Okay, don't put y top with x left, and it'll just be horribly wrong. Okay, people, that's the full question for that particular section there. So in the next video or two, I'm going to take another section which is a little more complicated, and I'm going to work through all of those questions over there so that you can get to understand a little better. Okay, people, that's it for now, and I will see you in the next lesson now. Yeah, I'll see you in the next lesson.